Before there was Earth, there was the Sun, the anchor and gravitational heavyweight of our solar system. Long before our planet or the Moon existed, the Sun formed from a swirling cloud of gas and dust called the solar nebula. The Sun ignited first, gathering most of the material, while the leftovers became planets, moons, and asteroids. Earth and its neighbors are essentially the remnants of the Sun's formation. The Sun's gravity holds every planet in orbit, creating the stable system we call home. Without the Sun, Earth would drift into the cold void of space. The Sun is the heart and parent of every object in our solar system. When you look at the Sun, you're seeing the ancient, fiery core of our existence. It predates our world, forged it, and sustains it with every photon of light. The Sun is the beginning of our story, and the central character in the epic of our solar system. Everything else, including us, is part of its magnificent unfolding narrative. Our Sun is a star, one among billions in the Milky Way, but for us, it's the star. It's a massive ball of hot gas, mostly hydrogen and helium, with traces of heavier elements that make up our planet and ourselves. The Sun is enormous. 109 Earths could fit across its diameter, and over 1.3 million Earths could fit inside. It contains more than 99.8% of all the mass in the solar system. Its gravity keeps every planet, moon, and asteroid in orbit. A cosmic ballet with the Sun as the lead. Without this gravitational anchor, the planets would wander aimlessly through space. Despite its size, the Sun is a fairly average star, a G-type main sequence star, or yellow dwarf. There are stars much larger and brighter, and others much smaller and dimmer. The Sun's just right nature is crucial for life on Earth. Its mass and energy output create the conditions for a stable, life-supporting environment. We truly are made of star stuff, and the Sun is our direct cosmic ancestor. Its presence defines our solar system. And as we'll see, its stability is the reason life could take hold on Earth. The Sun is structured in layers, each with a unique role. The core is the powerhouse where nuclear fusion generates energy. Surrounding the core is the radiative zone, where energy bounces around for thousands of years before escaping. Next is the convective zone, where hot plasma rises, cools, and sinks, creating a churning motion. This movement brings energy to the Sun's visible surface. The photosphere is the surface we see, a thin layer from which most sunlight radiates. Above it is the chromosphere, a reddish layer visible during solar eclipses. The outermost layer is the corona, a wispy, superheated atmosphere extending millions of kilometers into space. The corona is mysteriously hotter than the surface below. Each layer plays a part in the Sun's energy journey from core to space. The Sun's structure is a dynamic system, not a static ball of fire. Understanding these layers helps us unlock the secrets of how stars work. And it all starts deep in the core, where the real magic happens. Deep in the Sun's core, nuclear fusion is the engine that powers our star. Temperatures reach 15 million degrees Celsius, and pressure is immense. Here, hydrogen atoms are stripped of electrons, leaving protons that fuse together. 4 protons combine to form a helium atom, releasing energy in the process. The missing mass is converted to energy, as described by Einstein's EMC2. Every second, the Sun fuses 600 million tons of hydrogen, converting 4 million tons of mass into energy. This energy travels outward, eventually escaping as sunlight. Fusion is what makes the Sun shine and sustains life on Earth. It's a self-sustaining process that will continue for billions of years. The Sun's core is truly the heart of our solar system. Earth orbits the Sun at just the right distance, the habitable zone. Here, water stays liquid, making life possible. Our average distance is 150 million kilometers, or 1 astronomical unit. Sunlight takes about 8 minutes to reach us. The Sun's energy drives photosynthesis, fueling the food web and producing oxygen. Its influence, combined with Earth's tilt, creates our seasons and shapes our climate. The Sun is not just a distant fireball, it's the force behind every living thing on Earth. The Sun's surface is a turbulent sea of plasma shaped by magnetic fields. Sunspots are dark, cooler regions caused by intense magnetic activity. These spots can be larger than Earth and often trigger solar flares, massive bursts of energy. Solar flares release radiation that can disrupt communications and threaten astronauts. Sometimes, flares are accompanied by coronal mass ejections, huge clouds of charged particles. When aimed at Earth, these can trigger auroras and even disrupt power grids and satellites. Space weather is a real concern in our technology-driven world. That's why scientists closely monitor the Sun's stormy behavior. The Sun follows an 11-year solar cycle, shifting from calm to stormy and back. This cycle is tracked by counting sunspots, which increase during solar maximum and decrease at solar minimum. Solar maximum brings more flares and coronal mass ejections, raising risks for satellites and power grids. At the peak, the Sun's magnetic field flips polarity. Afterward, activity wanes until the next cycle begins. Understanding the solar cycle helps us predict space weather and protect our technology. The cycle has been observed for centuries, but its variations are still being studied. The Sun's rhythm shapes the environment of the entire solar system. Stars have life cycles, birth, life, and death. Our Sun formed 4.6 billion years ago and is halfway through its stable main sequence phase. It will keep shining for about 5 billion more years. When the hydrogen runs out, the core will contract and the outer layers will expand. The Sun will become a red giant, possibly engulfing Earth. Its surface will cool and redden, but its luminosity will increase. Eventually, the core will run out of fuel and collapse into a white dwarf. The outer layers will drift away, forming a planetary nebula. The white dwarf will slowly cool over trillions of years, fading into darkness. This is the Sun's ultimate fate, a natural part of the cosmic cycle. Its death will enrich the galaxy with heavier elements for new stars and planets. The Sun's story is dramatic, but it's the fate of all stars like ours. Our solar system's future is written in the life cycle of our star. For centuries, the Sun was a distant mystery. Now we send spacecraft to study it up close. NASA's Parker Solar Probe is flying through the Sun's corona, protected by a revolutionary heat shield. It's helping us understand why the corona is so hot and what drives the solar wind. The Solar Orbiter, a joint ESA-NASA mission, will image the Sun's poles for the first time. These missions, along with the Solar Dynamics Observatory, are transforming our understanding of the Sun. They help us predict space weather and protect our technology. We're no longer just observing the Sun, we're exploring it, driven by human curiosity.